There is another way that one can measure the friction coefficient, which is way more complicated, and really that's not the reason why I want you to see it. The reason why I want you to go with me through these arguments is that you begin to see how subtle and how really difficult friction is. I'm going to put an object now on an incline, again, as we did before, and instead of having it sit on its own, I'm going to attach to it a string. So here is that object, and here is a string, and a pulley, and here a string. And here is an object, mass m2, and this object has mass m1. And the angle here, alpha. I'm looking for my green chalk. I want to use the same color convention. Now, let's look at all the forces that we can think of. Here is m1g. Let's decompose that in y and x direction, and I will call this direction y, as I always do, perpendicular to the surface. So we call this y. And I will call this direction now the positive x direction. You're free to choose it any way you want to. The force here is m2g. And now comes a major problem. The biggest problem is that you do not know in advance whether this system will start to accelerate in this direction, or whether it will start to accelerate in this direction, or whether it will not accelerate at all. This is quite possible. And all these three cases, as you will see, have to be dealt with independently. You cannot do it with one equation, as you will see. Let's first decompose this force, as we did before, in the y direction. So this one equals m1g cosine alpha. And this one, the x component, which is in the minus x direction now, equals m1g sine alpha. Clearly, this one, m1g cosine alpha, we never have to worry about. There is no acceleration in the y direction. So this normal force n will kill this one, and this is m1g cosine alpha. So you never have to worry about the y direction. We know there's no acceleration. We only deal with forces in the x direction that are of interest. There is a tension in this string. And now comes the problem. I do not know in what direction the frictional force is. If this object has the tendency to go uphill, which I don't know yet, then the frictional force is in this direction, because it opposes always the direction in which the object wants to go. If, however, this object wants to go in this direction, which I do not know, then the frictional force has to be put in this direction. And I don't know that. The only thing I do know is that the maximum value of the friction will be mu static times n, which is what we had there. Remember, that's the maximum value that the friction can have, times m1g cosine alpha. That I know. So now, if I want to deal with this, I have to look at three complete different situations. Acceleration in this direction, in which the friction is pointing here. Acceleration in this direction, in which the friction is pointing there, or no acceleration at all. There's also, of course, the tension here. And this tension is exactly the same as that tension. We discussed that last time. I will not go over that because this is an ideal and, of course, an unphysical situation. The pulley has no mass. The pulley is completely frictionless. And the string has no mass. It's a massless string. And I argued last time that, therefore, the tension here must be the same as the tension there. We even know the tension. I'm going to evaluate, for now, only situations that the system is at rest. It's not yet moving. If the system is at rest, t must be m2g, because this object is not being accelerated. So we already know that all situations where the system is at rest, T must be M2G. That's non-negotiable. It's this T as well as that T. Now I have to start splitting in the following situation. My first option is that I make the assumption that the system is just about to start accelerating upwards. It isn't doing it yet. It is just about to do that. If that's the case, then I know that the frictional force will be in this direction, and it will have reached the maximum value with the static friction coefficient. Now I can write down in the x direction Newton's second law. Now I have T, which is in the positive direction, minus m1g sine alpha minus f max. That now has to be 0. Just at the moment that it is just about to change its mind and start accelerating. Now I know what T is, that is m2g. So m2g equals m1g sine alpha plus the maximum frictional force, which is this value. So this is just at the moment that it wants to start sliding. Therefore, if I make mass m2 a hair larger, just a hair, it will go. And therefore, the moment that I make this a larger sign, I know that it's going to accelerate uphill. That's the criterion for going uphill. Now, I look at situation 2. Now I make the assumption that the object, still standing still, is just about to start accelerating downhill. Aha! If that's the case, I know that the maximum force is now pointing upwards. The same magnitude, but it has now a different direction. So now I can write down Newton's second law. So the frictional force is now helping T. So now we get T plus F max minus m1g sine alpha equals 0. We know that this is m2g. So m2g equals m1g sine alpha minus f max. Notice the difference. There's a plus sign here, there's a minus sign here. This is, the object is still not moving, but if I make m2g a hair less, just a teeny little less, it will definitely start to accelerate downwards. So if I make this smaller than sign, the object will start accelerating downhill. This is condition 1, this is condition 2. If the condition is neither 1 nor 2, what do you think will happen then? It's very possible that you don't meet any one of these two conditions. What do you think will happen? Can't hear you. It won't move. A is 0. Because these both cases is going to accelerate. So in all other cases, the acceleration equals 0. And the frictional force in this case will adjust itself just the right way so that Newton's second law in the x direction will give you for the force a 0.